In this video, we will study several more related rates problems. So the first example, a water tank has the shape of an inverted circular cone. So what do we mean by inverted circular cone? So a water tank is going to look something like this. And what we are told is that a cone with a base radius 2 meters and height 4 meters. So at the top here, the radius is going to be 2, and the height is going to be 4 meters. If water is pumped into the tank at a rate of 2 cubic meters per minute, find the rate at which the water level is rising when the water is 3 meters deep. Okay, so water is being pumped in, and we have some water level. And let's think about what we know. Water is being pumped in at a rate of 2 cubic meters per minute, and the units are telling us what rate of change this is. Cubic meters measures volume. So what we know is that dV dt is equal to 2 cubic meters per minute. And what we would like to find is the rate at which the water level is rising when the water is 3 meters deep. Okay, so we have to think in terms of where this water level is. At the water level, there is a radius, call it r, and there is an associated height of that water, call it h. And what we would like to find is the rate at which the water level is rising. So that would be the rate of change of the height of the water level. And we want to find this when the height is 3 meters. So what we need then is an equation relating together the quantities V and H. And a common formula that we've probably seen in a past class would be what is the volume of a cone with radius r and height h. And that formula is that the volume is equal to 1/3 pi r squared height. And what we would like to do is implicitly differentiate this equation. The big observation to make, though, is that when we implicitly differentiate on the right, we're going to have a dV dt, or excuse me, the left. On the right, we are going to have to differentiate r and h both with respect to t. But we only know dV dt, we do not know dr dt. So that would be a problem. So my intuition is to rewrite so that it's only in terms of h. So rewrite so it's only in terms of h. And the big reason I'm coming up with that intuition is we want to find dH dt and we do not know what dr dt is. And there's a common technique that's going to help us here. And if we really look closely at our picture, we might see some similar triangles. So for the entire circular cone, you have this base radius 2 and a height 4. And associated with that water level, you have a radius r and a height h. So you have two similar triangles. And the key thing to remember is that when you have similar triangles, the ratio of their side lengths is going to be the same. So that means that in this case, r over h is equal to 2 over 4. So that is the radius is equal to 1/2 of the height. And we're going to go ahead and take this value, the 1/2 h, and we're going to substitute that in for r in the equation that we have for the volume. So when we do so, we are going to think about r as being replaced with 1/2 h. So r squared is 1/4 h squared. 1/3 times 1/4 is 1/12. Then we have pi h squared times h. So that's h cubed. And this is really the most difficult part of the problem, seeing that we have these similar triangles, which allows us to express it solely, the volume solely in terms of the variable h. So let's go ahead now and differentiate with respect to t. So both the left hand and the right hand side we can differentiate implicitly with respect to t. On the left we have dv dt. And on the right hand side you're going to have a 3 come down from the h, so 3/12, or otherwise it's, go ahead and say 1/4 pi h squared dh dt. And then we think about what it is that we want to solve for. We want to know what is dh dt. So we need to multiply both sides by 4. So we'll have a 4 dv dt if we isolate that dh dt. And then we are also going to have to divide both sides by pi h squared. And now we're in an ideal situation. We want to know dh dt when h is equal to 3. So we can just plug in all of the known quantities. So 4 times dv dt, which is 2, over pi times h squared, so 3 squared. So that gives us 8 over 9 pi. And if we think of the units to go with this problem, well, it's a rate of change of height, so it should be meters per minute. And we should be able to see this from our equation as well. The 2 with the dv dt was in cubic meters per minute. The 3 was meters squared, so meters cubed over meters squared leaves us just meters. And we have the desired rate of change. So one last problem dealing with related rates. And this problem is going to contain one spot that's a bit more difficult than the previous. So as the sun sits behind a 120-foot building, the building's shadow grows. Okay, so let's draw a picture representing this situation. So we have our sun, and we have the building. And as that sun sets, we think the sunlight is going to cause a shadow. So it's a 120-foot building. And what we would like to determine here, how fast is the shadow growing when the sun rays make an angle of 45 degrees? Oh, wow. Okay, so the shadow is going to be right here, cast by the building. And we would like to know the rate of change, how quickly that shadow is growing. So let's go ahead and let x represent the length of the shadow. And then we're told when the sun's rays makes an angle of 45 degrees. So we're thinking about the angle formed by those sun's rays coming down. Let's call that variable theta. So what we know is that what? It's a 120-foot building, and we want to determine the dx dt. So we want to find dx dt when that angle theta is equal to pi over 4. Now, looking at the picture we've drawn, we can easily come up with a formula relating x and theta. And thinking in terms of trig functions, you could say what? Tangent of theta is 120 over x, but that puts the variable x in the denominator. So it might be more convenient to say cotangent of theta is x over 120. So cotangent of theta is x over 120. Now when we differentiate both sides implicitly, we will get the dx dt, which we are hoping to solve for, but then we'll also have a d theta dt appearing. So do we actually know the d theta dt? And this is the part of the problem that I think is a bit tougher than the previous problems. We have to think about this a bit carefully. Do we know d theta dt? So it's this angle formed going from the sun to this point on the earth. And if we really think about this, I'm going to claim that we do. And the key observation to make is that the earth rotates once every 24 hours. So the earth rotates once a day. Well, we want our time unit not in terms of day, but in terms of seconds. So we have to say, well, how many seconds are in a day? Well, if we do the math, it's going to be 86,400 seconds, i.e. once every 86,400 seconds. That's how many seconds are in a day. So how would you get that? You would take, well, 1 day times 24 hours times 60 minutes per hour times 60 seconds per minute. And that will give you the 86,400. So the rate of change then is going to be how the angle changes with respect to time. Well, going one full rotation is 2 pi. And the time unit is 86,400. And this rate of change will be given in terms of radians for the 2 pi, and we're dividing by seconds. So this was, it's a very tough observation to make, and maybe not one we would expect you to just immediately come up with on your own, but something that we now have seen. So replicating this in the future should be a bit easier than the first time around, we'll say. So we now have everything we need. Let's go ahead and implicitly differentiate everything with respect to x. So when we do so, we have to remember the derivative of cotangent, one of these common trigonometric derivatives, is cosecant squared. We evaluate it at the inside function, and then we multiply by the derivative. So an implicit derivative, you differentiate exactly how you would like to, then multiply it by d theta dt. On the right-hand side, we are going to have 1 over 120 times the derivative of x with respect to t. So let's go ahead and isolate that for that thing we want to find, dx dt. It's going to be minus 120 cosecant squared theta d theta dt. And I realized at this moment that I forgot something earlier. If we look back at the d theta dt we came up with, that angle theta is going to be getting smaller as the sun sets. Because if you imagine drawing this over further, it's going to be a smaller angle. So my rate of change with d theta dt needs to be negative because theta is a decreasing quantity. And in a moment, I'll point out why I realized that observation. So now the thing that we would like to find, dx dt when theta equals pi over 4. So that's going to be minus 120 times cosecant squared of pi over 4 times d theta dt, so minus 2 pi over 86,400. Cosecant squared of pi over 4, Well, cosecant of pi over 4 is square root 2. So this quantity is square root 2 squared. So what we are going to end up with is a negative times a negative, so those go away. Then in the top we're going to have 120 times 2 times 2. So 480. And this is all divided by 86,400. And we have a pi in the top as well. So this simplifies to pi over 180. And what will our units be? Our units will be in terms of feet per second. Now, why did I notice that I had forgotten my minus sign previously? Well, dx dt, the length of the shadow is getting larger, so we should have a positive rate of change. So I have a minus sign. I need another minus sign to make that positive. So the observation was we do have that. It's because this angle theta is decreasing.